Hello and welcome to our 9 a.m. press conference, first results from the Norwegian Young Sea Ice Expedition. Our speakers today are Mats Granskog from the Norwegian Polar Institute, Vaughn Walden from Washington State University, and Amelie Meyer from the Norwegian Polar Institute.
Okay, thanks. Good morning. We'll start off with a video so you get into the right Arctic mood and we'll take it on from there.
Another warm day in the Arctic.
Another warm day, yeah.
Minus 27 and light winds for the day in the office.
Okay, good morning. I hope it was worth the wait. My name is Mats Granskog and I'm a sea ice scientist at the Norwegian Polar Institute, and I'm the chief scientist of this expedition myself and my colleagues will tell you about today. I spent myself almost 3.5 months out on the ice, drifting with the ice, and it was one of the most exciting field campaigns I ever took part in during my career. But it was also one of the most challenging to execute. But we did some very unique observations in the high Arctic close to the North Pole, from when it was pitch dark and cold in the middle of winter until the summer when the sun never sets. And it's these extremes that kind of define the Arctic in many ways. And a lot of the things we actually experienced took us by surprise. We saw a new Arctic, where the ice is much thinner, only 3 to 4 feet thick, and this ice functions very differently than it did 10 years ago, when the ice was much thicker. We were also surprised that there was so much snow on the ice, way more than we kind of expected from earlier work. But we also saw that the marine ecosystem in the Arctic was affected by this new Arctic. We observed the first and northernmost under-ice phytoplankton bloom very early in the season, when the ice was still snow-covered. And it was only this new Arctic ice, very mobile ice, that allowed this to happen. So we can say that this thinner and younger ice in the Arctic today works very differently than the ice we knew. It moves much faster, It breaks up more easily. It's way more vulnerable to storms and winds. But the loss of the Arctic sea ice will affect not only the local residents and conditions, but it will actually affect the weather far away from the Arctic. And we also found out that the observations we did during the campaign helped to improve weather forecasts in North America and in East Asia. The so-called Arctic amplification, the rapid warming of the Arctic, is in part a result of the drastic reduction in Arctic sea ice we see in the last decade. And this has already influenced the weather and climate patterns on the planet. It's disturbing that the accelerated warming in the Arctic actually feeds more warming in the Arctic and can result even in more drastic changes. And these drastic changes in the Arctic sea ice kind of calls into the question the knowledge we have today about Arctic sea ice. What's the validity of the many descriptions we have in computer models today that predict the future? And this was one of the main reasons we actually went out there, to find out how well do we actually know the Arctic. And as you saw from the video, we had to battle the dark, the cold, violent storms, ice that broke up under our feet many times, so we had to escape from the ice and rescue our camps. We had to look out for polar bears who look friendly, but not always aren't so friendly to us or our equipment. So it was no simple ordeal to go out there and do this. And over 70 scientists from more than 10 countries took part in this expedition. You might wonder why, but it's pretty obvious that the changes in the Arctic will affect everyone on the planet. So understanding how the Arctic functions and to be able to predict its future is very important for us. I'll now give the stand to my colleagues who will give some more information on the main findings we had during the campaign.
Good morning. My name is Vaughn Walden, and I'm a professor of civil and environmental engineering at Washington State University, where I work at the Laboratory for Atmospheric Research. My role in NICE 2015 has been to help characterize the atmospheric conditions over the sea ice. I spent about a month on the ship, and it was my first experience on sea ice, and it was also the most exciting field experiment I've ever done, and I've been to a lot of cold places. Everything that I encountered was new. Here are some of the results that me and my colleagues have found, and today I'm going to focus on the winter measurements only, because these are the results that are the most novel, at least from the atmospheric point of view. So the NICE 2015 field campaign was only the second time that observations have been made over the central Arctic ice pack in winter. The first observations were made almost 20 years ago during the Surfaced Heat Budget of the Arctic Ocean, or SHIBA, field campaign. SHIBA was conducted in the Pacific sector of the Arctic over thick multi-year ice, and in contrast, the NICE 2015 field campaign made the first winter observations in the Atlantic sector of the Arctic Ocean, but also the first measurements over young, thin sea ice. So the measurements from the Arctic winter are quite rare. They're very difficult to obtain because, quite honestly, it's dangerous work. I was on the ship in the springtime when it was relatively warm, but my colleagues really had to endure incredible conditions to take these measurements that now help us to understand the new Arctic. Some of the NICE observations actually reinforce what was learned during the previous SHIBA campaign 20 years ago. Despite the overall warming of the Arctic over the past several decades, our results show that the atmospheric conditions during SHIBA and NICE were in some ways similar. Both campaigns measured that the winter Arctic atmosphere tends to either be clear or overcast, without a lot of broken clouds in between. And this supports that this is a feature across the entire Arctic. Also, our observations of the atmosphere when it was clear and cold were somewhat similar to SHIBA. However, our measurements of the overcast and cloudy conditions were quite different. In fact, our team observed conditions that had never been observed in the Arctic before. Specifically, these conditions were related to significant storms that passed over the ship on several occasions, kind of one after another in the winter. With the help of model simulations, we know that these types of storms occur at this location in the Arctic, but the N-ice measurements are unique because no one has ever ventured to this location at this time of year to make these unique measurements. These storms were carried over the ship by an unusual jet stream. This jet stream had an anomalous north to south trajectory that had the effect of steering storms generated over the relatively warm North Atlantic Ocean into the high Arctic and over the study area. These storms brought warmth, moisture, clouds, precipitation into the high Arctic. But the winds also pushed the sea ice, contributing to the lowest maximum sea ice extent ever measured in winter in the Arctic, which occurred in February. It occurred early in February of 2015. This type of wavy jet stream is consistent with our current understanding of how Arctic amplification may be affecting and in part creating the new Arctic. So now let me present some specific results. One winter storm in early February raised the surface temperature from -40 Fahrenheit to 32 Fahrenheit in less than 48 hours. During this time, the wind speed went from calm conditions to over 50 miles an hour. The moisture in the air increased by over 10 times. And also, the largest snowfall of the entire 6-month campaign occurred at this time. In general, as Mats alluded to, the amount of snow on the sea ice during this campaign was greater than what is considered normal, which was a surprise to the researchers. However, much of the snow had actually fallen earlier in the winter before the start of the field campaign. In spite of its importance, there is still a lot of uncertainty about the depth of snow on sea ice across the Arctic, and so the N-ice measurements are quite valuable in this regard. These winter storms also have large effects on the younger, thinner sea ice. The high winds create a lot of stress on the ice and push it around and break it up. The large amounts of heat and moisture greatly affect the balance of energy at the surface, and because it's relatively warm, they restrict the growth of the sea ice. In addition, the significant amount of snow insulates the sea ice from the atmosphere. The N-ice field campaign also documented the transition from winter to summer for only the second time, and in the spring and summer conditions were more normal than the winter. When the sun returns in the spring, solar radiation becomes an important source of energy that helps to melt the sea ice. But because the sea ice in the new Arctic is so much thinner, it takes less energy to melt the ice than it did only a few decades ago. Scientists still have a lot to learn about the Arctic. Researchers have consistently underestimated how rapidly Arctic sea ice will decrease as a result of significant climate change in this region. Part of this is due to the fact that there are so few observations during critical times of the year, including the winter, and the transition seasons when the young, thin ice is either forming or decaying. The observations made during the N-ice 2015 field campaign have provided valuable information as to how the atmosphere affects the sea ice in various ways. And so now Dr. Amelie Meyer will tell you about the perspective from underneath the ice.
Hi, good morning. My name is Amelie Meyer. I'm an oceanographer at the Norwegian Polar Institute in Norway. In 2015, I spent 12 weeks on board the research ship the Lancer that you can see on the photo here over several trips. You've heard a lot about the storms that took place and how they affected the ice. I can now tell you a little bit about what was happening under the ice in the ocean. So the Arctic might be a cold place, but actually the Arctic Ocean is relatively warm. Even when it is -40 degrees Fahrenheit outside, the water below the ice is only about 32 degrees plus Fahrenheit, and a few hundred meters below the surface it can reach +40. This warm water is usually a few hundred meters below the surface, below the ice, so it doesn't usually reach it up, and the heat doesn't make it to the ice and can't melt it. What we wanted to work out when we were out there was how often, how much of the heat comes from the deep to the ice and melts it. Here we found that the storms actually played an important role as well. So you have to imagine the Arctic Ocean below the ice as a quiet place. The ice on top of it isolates it from the atmosphere, and as a result, there's very little movement in the water, as is shown on this picture. This helps keep the warm, heavy water deep and the cold, light water just under the ice. During NICE 2015, we found that when storms came through, it made the ice drift so fast that it actually stirred the water under the ice. This helped bring warm water from below much closer to the surface and actually induce some melt of the ice from below. In winter, the ice melted a few inches from below, which is already significant when you only have a few feet. But in summer, the numbers were just huge, with as much as 10 inches of ice melt a day from below. When you're standing on just 3 feet of ice, that doesn't give you many days before things become a little interesting. This is our camp in June 2015, as seen from the ship. You can see a few tents, a few people working. We had different sites on the ice, a few hundred meters from the ship. Some people were working even kilometers away from the ship. These tents usually gave access to the ocean or to the ice through holes. We had instruments deployed, sampling. We had computers, for example, in the little white hut on the left-hand side. We had a power cable going from the ship all the way to these tents to provide power to the instruments, and we commuted either by walking or driving ski-doos, as you saw in the video. At this stage, the floe is a few miles wide. We know it's melting already, and we're trying to understand exactly what's melting it. You know, is it coming from the heat from the atmosphere because we're going into summer? Is there something happening with the ocean as well? So we have all our instruments out there, but we know it's melting fast. And we need to make sure we're not going to be on there when it actually breaks up. Now, this is the morning of the 19th of June. Very early, a crack appeared as we were all waking up and heading for breakfast. Luckily, nobody was out there. In the background, you can see these white and red tents that's on the previous picture. You see it's quite far away from the ship, and we're now separated from it. So we just had some people quickly run down the gangway to pick up whatever was close to the ship. Within 10 minutes, it was like this. Another 10 minutes, things starting drifting out. At this point, this is just only half an hour after it started. We're still just trying to work out what's happening. And we say, okay, we got to go and collect everything. It's going to pieces really quickly. So a rescue team of just a handful of people, and I was part of that team, went out on a small little Zodiac boat. We were wearing survival suits. And we had to hop on from one little bit of ice to the next to try and recover everything. A lot of the instruments have the data on them. So if we lose the instrument, we lose everything, all the data we've been working for. Within a few hours, this is what was left. So we went from a few miles wide piece of ice that was, you know, melting but looking really stable to just this, hundreds of pieces. We spent half the day going around collecting. It was a little epic. A few times, I have to admit. But we did recover absolutely everything. And most importantly, we did recover that data. Now, the warm water from below doesn't just bring up warmth to the ice and melts it. It also brings up food to all the Arctic life that's under the ice. These small algae and plankton play an important role in the carbon pump of the Arctic and of the planet. We found that the thinner and more dynamic Arctic ice actually promotes light transmission through the leads or cracks in the ice. So if you have more cracks in the ice, you end up having more light underneath, and this promotes life growth. So we ended up observing a really big bloom that Matt mentioned earlier under the ice really early on, which was a first with so much snow around. One could imagine that having more algae and more bloom would mean more carbon export, which is part of the carbon pump. So you imagine if you have more algae breathing and taking up carbon, they will store it into the ocean, and it helps taking out some of this CO2 out of the atmosphere, which is an important part of climate change. But as it turned out, the algae that grew in these blooms didn't sink very well, which meant they stayed close to the surface. Which just means that in the end, these blooms that we saw didn't really contribute to the export of carbon to the deep ocean. and such changes in the under-ice blooms could have important implications for the Arctic carbon pump. So really what we saw out there was really fragile sea ice that was damaged by storms that could be more easily melted by the atmosphere and the ocean. More cracks and opening in the sea ice is making it possible for life to grow sooner under it. This will lead to large changes in ecosystems and have a large impact on Arctic fisheries. The ice retreat and changing dynamics is already opening new shipping routes around and through the Arctic. This will put a fragile region already undergoing drastic changes under even more strain. And this photo was taken right at the end when this floe broke up completely. We still had a few days of ship time. And instead of just leaving, we decided we'd keep following these little bits of ice and keep studying them to see how much smaller we're going to get and what was going to happen. And these polar bears just came and followed us for a few days. There we go, that's it. Thank you.
Okay, thank you. We will now take questions from any reporters in the room. Please raise your hand and state your name and affiliation. Are there any questions from any reporters in the room? Are there any questions on the chat? No? Okay. Here we go.
Could you go over for us the amplification and sort of feedback so that we all clearly understand that process?
Arctic amplification is a process by which, when we introduce carbon dioxide into the atmosphere, it creates a greater greenhouse effect, which creates warming, something that it's very clearly happening. But what it does is it makes the air temperatures warmer, and that has a tendency to melt the sea ice. This is also what we're observing. We're seeing, decreasing sea ice at all times of the year now. As you melt the sea ice, the solar radiation from the sun is able to be absorbed by the ocean water, whereas before the ice reflected it, because the reflective properties of ice are much higher than the reflected properties of ocean water. So this creates what's called a positive feedback, or an amplification of the warming. And what this was predicted decades ago by the earliest climate models. It's a process that we know quite well, and it just, as we introduce carbon dioxide in the atmosphere, it warms the planet, but then the sea ice albedo feedback is what they call it, amplifies the Arctic warming. So we're seeing a higher rate of warming in the Arctic than we do globally. There are other things that happen after the ocean starts to absorb this warmth. Then you have a warmer ocean, which also tends to melt more sea ice, and there are a number of cascading effects that cause this amplification that are specific to the Arctic region.
Are there any other questions? Oh, here.
Just wondering what else was, Madeline Nash, freelance, what else was going on in the atmosphere that might have made this particular time frame either anomalous or representative of the trend at large? Perhaps you could address that.
Sure. We've looked at this a bit, and there were some anomalous pressure systems set up in the winter. There was a high pressure kind of over Canada, and it came down quite far south. And because of that high pressure sitting over Canada, it caused the jet stream to have what's called a meander in it, a large swing in it, which basically caused the air trajectories, the storms, to go south to north. And those types of storms bring a lot of, as I mentioned, a lot of warmth and moisture. So that was definitely the way that the atmosphere was set up during the months of the winter that we were there. That would be January and February of 2015.
Harvey Lyford, freelance.
My question is a bit related. This was only the second and maybe really the first time something like this has been done so far north, if I understood you correctly. And therefore, you don't have any data to compare it with, I would guess, from previous years or decades. And I'm wondering how you know what is changing based on this one set of observations. I'm not sure I'm being clear, but we know the Arctic is warming, but the specifics that you've studied and observed, how do you know how different it is from decades past?
I can answer that.
Jeff, go ahead. I have a
So
perspective.
it's a really good question, actually, because when we say how things are changing, but it's the first time we go and look at it, that's kind of your point. How do we make that point? So we were there for 6 months. The winter data is what was really rare. So out of the 6 months, we do have a lot of things to compare with past February. So from March onwards, there has been a lot of observations done in the Arctic, both for the ocean, the atmosphere, the ice. Maybe not so much the snow. The snow is a bit of an unknown. But for the ocean, the ice, and the atmosphere, we have data past February to compare with. For January and February, the data is much rarer, but there are a few points. It's just that no one had gone and been there for days on end, measuring the change from one day to the next. Does that answer your question to a certain extent? Yes?
There are other ways to observe the Arctic other than being on a ship frozen into the ice. We rely on other means of measurements, for instance, satellite measurements. So satellite measurements give us very good measurements of the amount of sea ice and how it changes seasonally through the year. And we also have good satellite measurements of the atmosphere. So, and those are year-round, of course.
Are there any other questions in the room? Okay. You could please state your name and affiliation.
Nick Shapiro at University of Oklahoma. Did you find any cool details in the snow and ice profiles that you were taking?
Can you be a bit more specific? What type of profiles?
Turn your mic up.
So yes, there was a lot of really interesting findings. There is a special issue in the Journal of Geophysical Research, GRL, that we've submitted a few months ago. Papers are coming out, and in the audience we have actually some specialists. So if you want to speak to the snow person, we have one here. We also have the ice postdoc here who can answer some questions. They're just sitting in front of you in the row or two. So just go and talk to them if you have some specific questions.
Mats Granskog, I can say a few things. As we said, we found a lot of snow, which was surprising to us. And this snow causes the sea ice actually to float below the sea level and flood the ice with seawater, which is kind of unusual for the Arctic, we believe. It hasn't been observed a lot before. And we saw a lot of that, which means that this slush that formed from the mix of seawater flooding on the bottom of the snow and that freezing was kind of a new, neat thing we observed. So that's a process that happens a lot in the Antarctic, where the ice is much thinner and there is more snow, but it hasn't really been kind of observed in the Arctic before. And partly it's because there's very few observations, but I mean, from what we understand, that's not really the normal Arctic from earlier days. If that answers your question a bit.
Are there any other reporters in the room who have questions? Are there any questions on the chat?
No questions here.
Okay, that concludes our press conference. Thank you very much.